Hello and welcome to Embedded. I'm Elecia White here with Christopher White. I remember I've been asking guests for lightning facts. It hasn't been going so well. But this week, I expect it to go very well. Our guest is Eric Brunning, and he's an expert on lightning. Be prepared for a shocking episode.
Hi, Eric. Welcome to the show.
Hi, thanks for having me.
Could you tell us about yourself as though we just met after John Lehman's Geocast podcast?
Yeah, sure. I work at Texas Tech on the faculty. I teach in an atmospheric science program, and grew up in Wisconsin originally, and did my graduate work and undergraduate as well at the University of Oklahoma, and spent a couple years in Maryland after finishing my PhD, and wound up in sunny Lubbock, Texas.
Studying lightning.
And meteorology, yeah.
Cool.
Texas is probably a good place for that.
Yeah.
It is, yeah. It's nice to live in the place that has the thing you want to study, and lets me run an instrument here and get graduate students involved in that instrumentation work.
So now we want to do the thing that has been getting us into trouble, which is lightning round, where we ask you short questions and we want short answers.
Okay.
Christopher, do you want to start?
Sure. Benjamin Franklin and the kite. Thought experiment or write-up of scientific apparatus?
Write-up of scientific apparatus.
Back to the Future. Thought experiment or write-up of scientific apparatus?
Thought experiment.
Ball lightning. Fact fiction or the coolest thing ever?
Fact, probably.
Sprite. A diminutive ethereal creature, a two-dimensional bitmap that is integrated into a larger scene on computer graphics, or a weird thing that happens above clouds?
Yes.
What is the most shocking fact that you know?
Oh boy.
That's what you get for letting me write these.
Do I go with a pun or not? I guess that's the question here. Let's see. Lightning is many thousands of volts.
Oh, that is a shocking fact. It's good that somebody knows that.
Yeah.
If you were playing Legend of Zelda, and it was lightning around you, would having the rubber pants actually help you as you were standing in the lake? Or would rubber pants not really do anything?
Probably not help you too much.
Okay, if we got the rubber pants, the rubber shirt, and the rubber boots.
The helmet, too. There's a rubber helmet.
Oh, okay.
Yeah.
I'd rather be in a metal cage.
All right.
Okay, so let's get on to some more detailed and possibly useful questions. Let's see. Do you want to talk about your career first, or do you want to go through the list of many listener questions about lightning?
Well, we can, I guess, start with career since we just did the meet and greet.
Okay, so you work on lightning detection as well as meteorology.
Yeah, that's right. My degree is really in meteorology, and that makes me a little bit unusual in among scientists that study lightning. A lot of folks, I think, get into it from a physics or electrical engineering background because the instrumentation's relatively straightforward to build, and it's a kind of fun phenomenology to study from that point of view. So my degrees are all in meteorology, and worked in a lightning research group at the National Severe Storms Laboratory. And that, so I kind of got into it sideways and almost by accident. As an undergrad, there was a research position available, and I got involved and never really left.
Okay, so how do you detect lightning, assuming it doesn't hit you and it's more than 5 miles away?
Right. It's primarily detected as with various bands in the radio frequency spectrum, and so depending on which part of the lightning process you want to detect, you can listen for lower or higher frequencies with a radio receiver, or there's even simpler versions of that, simply involving digitizing charge that comes off of a metal plate.
So the radio receiver, I have heard like more AM than FM, but AM radio gets really glitchy and staticky in a lightning storm.
Yeah, it absolutely does. Lightning's a very broadband emitter in the radio frequency spectrum. I always think of it when I read those FCC warnings on the back of electronics, and because AM is allowing you to listen directly to the amplitude of the radio signal in that band, you can very readily pick up then the noise produced by lightning. And so if you want to do lightning detection scientifically, it's a matter of digitizing that noise fast enough to be able to resolve processes. And
it's a pretty high velocity impulse. I mean, we look at lightning and it flashes and it's very big. And when we hear it, it's a big bang if you're close enough. So it's very impulsive. Do you see that all across the spectrum?
Yeah, it's impulsive all across the spectrum. So the thing that you just referred to is what's called the return stroke that we see. It's the big bright flash of light when a lightning channel connects to the ground. So there's a whole lot of charge that's moved over a very long distance, heats up the air, and you see that bright flash of light and the percussive sound that goes with that very impulsive heating.
So there's more to it than just that. Lightning is not just that flash I see.
Yeah, exactly. So, if you go to the very high frequency part of the electromagnetic spectrum, so, tens of megahertz, and above, kind of right where the old, analog TV channels sit, at that, frequency band, the stepping processes are on a very small scale, tens to hundreds of meters, in terms of step length. And so if you sense in that band, you can map out the entire shape of the lightning channel. But that too is also an impulsive process and, essentially acts as a point emitter.
Okay. I sort of understand this. I used to work on a system that would find gunshots by listening to audio waves and locate them based on time difference of arrival to the different sensors. And one of the things that was really kind of pounded into me is sound moves at a certain speed. And if we get the sound speed wrong because of humidity or whatever, then we get the location wrong. And there's a very constant proportion to it. And so what you're doing is looking at a very, very high frequency, which would give you a finer grained picture of what was happening. Is that right? Am I getting the right?
Yeah.
Okay.
Yeah, that's right. And the time difference of arrival is the primary method that's used to do lightning detection. It's the instrument that I use mostly, uses that method. And so we don't have to worry quite as much about the propagation speed. There are some applications where that does matter, but certainly up in the VHF where it's propagating through the atmosphere, it's essentially treated as a constant speed.
So is it a pretty distinct signal, or are there kinds of other terrestrial interference that can get confused?
Yeah, it's so the instrument works by very naively digitizing the peak pulse that arrives in a typically about an 80 microsecond window, and that and so if you have a local noise source, say a power line or something that's sparking, that's going to raise your local noise floor and reduce your sensitivity to lightning.
Okay, I'm going to ask an off the wall question now.
Yeah,
my dad used to do ham radio, and I kind of do ham radio in the sense I have a license, but I don't do anything with it. But I remember as a kid tuning in to a particular band and having my dad tell me we were listening to lightning on Jupiter. And I looked it up this morning before the show, and that's all true. You can do that. It's a shortwave. There's a shortwave band.
Really?
And I was wondering if you may not know this because it's a kind of a weird thing, but is that in the same region or is it somewhere else? Could we be confusing Jovian lightning for Earth lightning?
Oh, that's a good question. Shortwave. So what wavelengths is that?
10 to 25 megahertz is the frequency.
Yeah. It's interesting. So that must somehow make it through the ionosphere as well. So I wonder, it's kind of an interesting thing that's even possible. So yeah, that's close enough that I guess you could be picking it up.
But ours would be louder.
That's true.
Terrestrial would be a lot.
Yeah.
more impulsive.
Yeah, I'm
sure
it's pretty weak by the time it gets here, even though it's much bigger lightning, I'm sure.
Yeah. So that's interesting. Although our antennas are probably not that much more sensitive than ham radio. Probably, maybe they're actually less sensitive. I'm not sure. I've never done any ham stuff, so it's possible you guys are picking up a smaller signal that way.
Yeah.
Okay, as long as we're on the topic of lightning in outer space, do you get lightning effects from the moon? I mean, do things bounce off the moon?
I have never looked into that.
Who asked that? One of our listeners.
Yes.
Interesting. I don't know if that would work or not. You'll certainly get radio frequency signals that'll propagate from the Earth upward to where you could detect them from a satellite. So, it's likely that if you were listening up on the moon, you'd pick that up. And so I suppose a signal could bounce off the moon. Again, it probably depends on if is there some other signal that's known to bounce off like that?
Yeah, I think there's been other moon bounce stuff that's been done.
Well, and then there's that neat video of Milky Way in radio waves reflecting off the moon. That was fantastic. So the Milky Way's own radio waves reflect off the moon, and if we point radio receivers towards the moon, we can image the Milky Way in radio spectrum, and it's just magical.
Here it is again. Ham radio operators utilize Earth, Moon, Earth for two-way communications. So people do use
That's really neat.
It's crazy.
Yeah.
Would you like us to go back to asking things you know about?
Well, you have to ask to figure out what it is that I do know about. I mean,
we're just giving you suggestions for papers.
Yeah.
I wish I had the time for all the ideas that are out there.
Okay, so you have a metal plate, if I heard right, and you measure very high frequency, and then what happens?
Okay, so the one that I was talking about in the very high frequency band, that's a regular dipole antenna. Actually, it's
okay.
So that's a different thing from the metal plate system. But we can talk about that metal plate if you want.
I think you wanted to just hear about the whole detection system, right?
Well, actually, no. The metal plate's kind of cool because I heard from someone that I could build my own lightning detection antenna with like a salad bowl and a pizza pan.
Who have you been talking to?
John Lehman.
Oh.
Yeah. So John and I have actually been working on a sort of prototype for this, and it's based on a design that really dates back to the 60s or 70s. It's a really standard atmospheric electricity instrument. I went out to my local restaurant supply store and looked for a pizza plate that you might use in a restaurant to serve or heat pizza, and found one that fit inside the opening of a salad bowl. And if you hook up a charge amplifier to the pizza plate and digitize that, you can detect lightning that way.
And salad bowl is ceramic or insulated?
It's a stainless steel or aluminum.
Okay, so they're both metal.
Yeah, that's right. So the salad bowl is really you can think of it as giving it a nice ground plane, just a nice sort of smooth shape that isn't going to concentrate the electric field too much, and usually hang it upside down so it also serves as a rain shield.
Okay, so now I have a salad bowl with the opening pointed down and a metal pizza pan. Also, now it's pointed towards the ground, but it's attached to the salad bowl through bolts, glue.
It's electrically isolated from the salad bowl,
so
and
hot glue.
Hot glue, whatever your favorite adhesive or any sort of insulator that'll just keep it separate electrically, and then the electric field in the atmosphere. There's always some background electric field, and then when charge moves around inside a thunderstorm, let's say there's a one of those big ground strokes, and a bunch of charge is moved very quickly. That changes the electric field very quickly. That induces a change in the charge on that metal plate because the electric field changed, and then the charge amplifier circuit pulls off that charge that's been induced, and that's proportional to the electric field change.
That sounds sort of like a capacitor. I mean, you have two metal bits, and then an insulator between them, and then you kind of just read what the charge is on this capacitor. Is that a reasonable mental model?
That's not a bad model at all. No, I think that sounds good.
And so what I'm measuring there is pretty simple. What does my amplifier have to look like then?
The audio on your question just dropped out there.
Oh, what does my amplifier circuitry have to look like?
It's an op amp and an RC circuit, and a little bit of signal conditioning, to reduce noise around that. But it's about the simplest circuit you could imagine.
And then an ADC and a little controller, and then a little warning inside my house that says lightning is coming.
Yeah, that's right. So, of course, you've got to digitize the voltage that's produced by that little circuit. So an ADC, and then, depending on how fancy you want to get, we've this version we've been testing is running at about 100 hertz, which is mind-numbingly slow. But if you get up into tens of kilohertz, you can resolve most of the important processes in Lightning, stuff that's happening inside the cloud before a connection is made to ground. And the sort of research grade sensors right now are in the sort of 1 to 10 megahertz digitizer range.
Okay. And you've said this before, the lightning stroke that hits ground, that's not all of what is happening. What can you walk me through how lightning happens from when there's not a cloud in the sky to when it hits the ground?
Yeah, sure. So once a cumulus cloud starts to build, the atmosphere gets colder as you go up. So as that cloud gets taller, you eventually start to get production of ice in the cloud. And it's collisions between precipitating ice particles called graupel and regular smaller ice crystals that are sort of like snow, very small snow crystals. Those collide with one another in the presence of supercooled liquid water, and the combination of all of that is enough to allow positive and negative charge to be separated, where the precipitating particle gets one sign of charge and the non-precipitating particle gets another sign. Then
wait.
Yeah,
why?
go ahead.
Why don't they stay balanced? I don't understand why they get separated.
Okay, so they you can imagine them starting as neutral, and when they collide with one another, a little bit of the ice surface gets torn off in the process of that collision, and the result of that is that one of the particles retains more of one of the signs of charge. And that's actually one of the great mysteries, is exactly what's going on at that ice surface collision. We have some idea from laboratory studies how to predict which sign of charge we're going to get, but there's PhD level work in refining that understanding.
So someday they're going to find out that little tiny ice cubes are walking around in their bathrobes, shuffling their feet against each other, and magic happens.
I think I'm going to teach it that way from now on. That's a great picture.
What's interesting, though, is it's a fundamentally an ice-based process, right? You think about thunderstorms as this summer event, barreling across the hot Southwest. But there's a lot of very complicated things happening in those thunderclouds with ice and rain and hail and lightning.
Yeah, that's exactly right. And if you can't make the ice, you typically don't get lightning out of those storms at all. There's been some very sketchy observations of lightning in what are called warm clouds, where there's no ice phase precipitation, but those are more anecdotal reports, and so it's really a requirement to have that deep cloud that gets into the ice phase. And
that's why with severe thunderstorms producing a lot of hail, that's okay, you're in deep danger of lightning.
Yeah, exactly. So the more of that precipitating ice you have, the more collisions you get, the more charges separated, and the consumption of that charge and reduction of the electrical stress produced by that charge being concentrated into regions that are perhaps a kilometer apart in the cloud is what leads to lightning.
So is it the ice cubes that are falling that are positive and the ice cubes that are staying that are negative, or the other way?
So there's actually a reversal line. It's about at minus 15 or 20 Celsius in the cloud, and below that level, the grapple tends to charge positive, and the ice crystals charge negative. And above that level, the ice crystals tend to charge positive, and the grapple charges negative. And
the grapple's what's falling, right?
The grapple's the precipitating one, yep.
Okay. Sorry, that leads.
Yeah, so that leads then to the basic electrical structure of a thunderstorm. It's called the normal tripole model, and it's a positive, negative, positive charge stacked in the vertical. And between each of those, you can think of them in a simplified form as charge layers. Between each of those charge layers, there's a large electric field, and when the electric field reaches a certain threshold, then you can get a lightning flash to start.
And so this is why we get lightning to lightning, or cloud to cloud lightning.
Yep, that's right. And yeah.
Where does the Earth come in? I mean, why does it go to Earth? What is Earth? What is ground? Sorry.
What is ground? It's a great place to dump a lot of charge when you have more that you need to get rid of than you can neutralize using the charge that's available inside the cloud. And so that's what leads to these ground strikes. Then is that it's energetically favorable energetically favorable to move all that charge to the Earth in order to neutralize the electrical energy in the cloud.
Okay, so you said energetically favorable, which actually leads to one of the listener questions. Mm-hmm. KBX81.
Fake name.
Clearly a fake name, not on the birth certificate. We've been talking about harnessing energy from lightning for a long time, and it's chaotic in its nature, but there's a lot of energy there. Why aren't we catching lightning to charge batteries?
So there's a lot of current there, but there's not a lot of energy. I would disagree.
Very short, right?
Yeah, it's a very short time process. Like you said before, it's very impulsive. So there might be in a typical ground strike tens of kiloamps for no more than a few milliseconds. In certain discharges, you can get something called continuing current, which might last on the order of 100 milliseconds or so. But the total amount of energy that's actually moved when you add up all that current over time is very, very small.
Okay, let's take the question the other way. Why is anybody working on harvesting lightning?
There are people working on that?
I've read about it.
Really? Huh. It's certainly not something I run into on a regular basis. And I think if you would survey the scientific community, they would say that's not a scientifically, just from scientific principles of what we know about how the energy is moved around in lightning is not a real likely to be a successful thing.
Yeah, it seems like we'd be better off harvesting an entire thunderstorm.
Well, yeah.
Just put up a bunch of giant windmills and go inside them.
Yeah. It's wind, solar, lots more direct ways to get the energy out of the sun converted into electricity.
But that's the thing I remember from working on lasers is a confusion between energy and power. Like a very powerful event might not dissipate a lot of energy, not comprise a lot of energy because it only happens over the course of a tiny, tiny, tiny fraction of a second.
Yeah, exactly. So lightning can still be very damaging. For a wind turbine blade, in fact, there's a whole lot of charge that's moved across the surface of the blade or through the interior of the blade, in a very short amount of time. And so that leads to heating, just like it does in the air that leads to thunder. And that can rupture a blade, but the total energy is not that large.
Okay. I believe that now. And having gone back to the Wikipedia page that is actually called Harvesting Lightning Energy, the first half is all about how people are doing it. The second half is all about how stupid that is. So I clearly should have read the whole thing.
Well, if you think about it, people get struck by lightning, right? If it was something worth harvesting energy from, it would vaporize people instead of killing them just most of the time.
Yeah, it's good. Yeah.
How often do people actually get struck by lightning as opposed to being near a lightning strike and believing they were struck by lightning? Have you ever been struck by lightning, or do you just believe you've been struck by lightning?
I can definitely confirm that I have not been struck by lightning, although it's been close when we were launching balloons into thunderstorms. And that's another whole fun story. But there's typically tens of deaths in the United States per year, and I know that a large fraction of those are actually from what's called a side flash or a side splash, are the terms used in the lightning safety community, where there's a sort of side part of the channel, not the main channel to ground, is what actually winds up affecting the person. And so the actual direct strike part of it is relatively rare. And that's why it's very dangerous to be standing under a tree, because if you're standing under a tree and that tree gets struck by lightning, there's a big potential difference between you and the tree. And so you get sort of involved in it by association.
That's a good euphemism.
Involved in it by association.
I was involved in a lightning strike by association.
Are there off-the-shelf lightning detection systems that people interested in it can purchase?
There's certainly are devices out there that will look at things like the electric field, or they'll look at the size of the radio frequency spheric, which is going to be proportional to current. And so if you assume that a typical lightning discharge has this much current, you can sort of infer the distance from that. If you're in the back country or something, it's great to be informed that there's an electrified storm nearby, so that you can, for instance, move to lower ground. For a lot of folks that are going about their day-to-day business, you can find a variety of weather apps that you can buy lightning ground strike detection maps as part of a subscription, and that's fairly affordable to do, so that you can actually see exactly how far you are from the nearest ground strike.
How far do the lightning strike signals travel? I mean, here in California, we don't get a lot of lightning. Can I watch your Texas lightning with the right antenna?
With the right antenna, you could. So there's a technique that can detect the very largest ground strikes that take place, the very highest current discharges, and you can build a worldwide network to detect lightning that way with about 6 sensors globally. So the lightning signal is at the right wavelength to propagate in the Earth ionosphere waveguide, and can make multiple trips around the Earth. And from that, you can geolocate then where that took place.
And the ionosphere's waveguide only works on certain frequencies. And this goes back to what you were saying about VHF and it being a broad spectrum impulse.
Yeah, exactly. Right. Yeah. So those big high current discharges, those are moving a lot of charge over distances of kilometers. And so they have a low frequency component that's very large, and that can then the channel actually acts as an antenna that is transmitting a radio signal at the right wavelength to be caught in that waveguide. When you get up to the what's called the stepped leader, it's the process of the lightning channel itself developing before a lot of current flows in it. That stepping process then is a smaller segment of channel. So just like with an antenna, the smaller the antenna, the higher frequency that radio frequency noise is emitted at.
Can I offer to build an antenna at my place and then find 5 other people to make a system?
Yeah, and in fact, that's what we do research-wise. I have some colleagues in Alabama, for instance, that were working on a project where they wanted to build one of these flat plate antenna systems, and so they needed to build that network, and they designed about 10 or 12 of those and set them up in backyards of graduate students over a county type area, and that's enough to then locate where those processes were taking place.
Is this what's known as lightning interferometry, or is that something else?
No, lightning interferometry, you have to change your culinary equipment there. That's usually done with a cake pan. And
is this how science works?
Yes.
I've heard that cooking is basically chemistry, so it's close.
Cooking pans are basically meteorology.
Yeah.
Yeah, I mean, it's a nice, well-manufactured, flat, cheap way to get a shape that you need. And so instead of having some custom part machined for you, you just go shopping at your favorite local restaurant store. And so, yeah, lightning interferometry, that's done with a very short baseline. Maybe 100 meters would be a very large spacing between the antennas. And the way you do lightning interferometry is it's sort of an extension of the time of arrival idea, except that you're digitizing very, very quickly, like at let's say 180 megahertz, the charge that's being induced on your cake pan. And so you do that very carefully with a very very fast digitizer, and then you run that. And then you look at the interference pattern produced by the signals from each of the antennas for the bright spot that was produced by a lightning channel as it develops. So that essentially becomes then a high-speed camera view of how lightning develops as depicted in the VHF band.
Why? Okay, this is. I know we're in the details, but I'm going to ask a meta question. Mm-hmm. Why study lightning at this level of scrutiny?
Other than it's really damn cool.
Yeah, well, that's
right. I mean, and I think that's what motivates a lot of us, to get interested in it, is that it's a basic science thing that's really interesting, and uses all that stuff from physics too that you were wondering what you were going to do with, since everyone else was talking about Newton's law, and so yeah, I mean, we're just interested in it as curiosity to start with. But, if you want to talk about understanding lightning safety or lightning protection for a building, you need to know how much charge is moving in that lightning discharge and is likely to be transferred to the building. And that allows you to then spec out a system for protecting the building. Some of the more recent applications, now that we can really, as computers have gotten faster, it's allowed us to detect lightning much more regularly and much more easily. And so that allows us to then do continuous monitoring of lightning, and that allows us to get into meteorological applications. So we can infer that the storm is intensifying because if we see more lightning, we wind up seeing. We can infer then that the amount of ice production in that storm is larger, and that allows us to infer that the storm's updraft is stronger, and all of the rest of the storm, all of the rest of the thunderstorm processes are really driven by the updraft and the precipitation that forms in it. So we can the U.S. National Weather Service is now very, very interested in understanding all of these details how lightning production changes with time as a storm's processes evolve throughout its life.
Can lightning help you predict when a storm is coming, or are other methods more reliable?
Yeah, I think the data has gotten really quite nice now to where we can map out the entire extent of the lightning in the cloud and even all of the branch channels, and make a distinction between these really big extensive flashes and really tiny flashes that are discharging tiny pockets of charge in the storm's updraft. And you can make pictures from lightning data that look very much like a weather radar. And so you can certainly do storm tracking that way. And in fact, for instance, in the western U.S., where there's mountainous terrain, it's very difficult to locate a weather radar there in a way that will allow you to comprehensively see where all the storms are. And so NOAA, the U.S. weather agency, and as part of the Department of Commerce, just launched a geostationary weather satellite that has an optical lightning detector on it that is going to allow us to really serve that purpose of detecting all thunderstorms comprehensively over that satellite's full disk field of view.
And then that will basically, to answer Christopher's question, predicting weather saves lives, protects crops. There's a reason why we pay for it.
Yeah, that's right. So, your forecast model needs to know where thunderstorms are taking place in a weather forecast model, and one of the applications of lightning data there for improving routine weather forecasts is to ingest that lightning data to say the atmosphere was overturning in this part of the world, and that's a sort of part of the atmosphere's energy budget that we need to account for. And so you can pull that lightning data into a forecast system and use that to refine that system's depiction of the state of the atmosphere.
Okay, I want to go to a question from Nick, the Exploding Lemur. What characterizes a lightning strike? What looks like a lightning strike but isn't? There's more to it, but I think we should start there.
What?
I mean, we talk about lightning strikes and all of that, but there's all kinds of lightning, and there's all kinds of lightning processes that happen before the strike hits the ground.
Oh, I see.
Yeah.
What is lightning again? Could we start there?
Yeah, but I'll go all the way back. Right. So it's a spark, but there's lots of different parts of that spark. And so, we talked about the lightning channel developing, and those are called stepped leaders. And as those stepped leaders develop, even before they make a connection with the ground, and this is how the in-cloud flashes work all the time. Once you have a channel network that's developed sufficiently, it's kind of a double-ended tree structure, and charge can move back and forth between one end of the tree or another to rebalance, how the charge is configured and minimize the energy imbalance. And so any sort of larger charge flow along that channel network is going to light up the cloud, and you would see the cloud light up, and we would call that lightning. And sometimes you can even hear thunder from that. And then as that channel sometimes will step down towards ground, and when it makes that connection, then you get these ground strikes, and that's another part of the lightning process that we would characterize.
I've heard from pop science occasionally that lightning doesn't go from the cloud to the ground; it goes from the ground to the cloud. Does that have any meaning at all, or?
Yeah, so that's a super fascinating story in terms of scientific communication. So, when you have almost all ground strikes that you see start by a channel that's developed somewhere in the cloud, and it's stepping down towards the ground. And when that channel connects to the ground, then there's a potential wave that develops from the ground and goes back up into the cloud. And that's what results in the heating and thunder and what you would sort of consider the human sensible phenomena that's associated with a ground strike. But there was when that study was done, I believe it was sometime in the 90s, that sort of demonstrated that there was this potential wave that propagated back upward once that connection was made. That got sort of picked up by media and described as, lightning goes from the ground up to the cloud. But that left out the entire part of the story where the lightning channel developed to make the connection with ground in the first place.
I'm going to make that my ringtone, what he just said. And then I'm going to have another one that says, well, actually.
I asked for it.
No, that was great because we do get pop science miscommunication. Exactly.
I always pick something hooky to try to, and often the real science gets lost in the, did you know that what you think is really this is that?
So back to the Cakepan Interferometry.
Mm-hmm.
Words I never thought I'd say together. You said 100 meters apart. That's not very far when you're talking about light or high frequency. I mean, it's far for a high frequency signal. It just doesn't seem very far apart if you're doing time difference of arrival sort of things.
Right. And for a time difference of arrival, you want 20 kilometers or something like that to really to make that work the easiest. But when you're doing that 100-meter spacing, that's going to be you're focused on aligning individual sort of fluctuations within a continuous signal that's fluctuating at some tens of megahertz. And so there you don't want as much time difference between those peaks, or because you're digitizing so fast, you don't need as much separation in order to distinguish processes from one another.
Yeah, in fact, it works against you to have too much distance with interferometry. You want to have a few multiples of a wavelength, which 100 meters sounds about right.
Yeah, exactly.
And if you were trying to do interferometry and you had a storm on two sides, not that you were in the middle of a storm, but you had one storm off to the left and one storm off to the right, would it just give you garbage data?
No, you would. So the way the data is often displayed is it's you can imagine a hemispheric dome above the interferometer, and then that's projected down onto a flat plane. And so if you had something happening to the left of you and to the right of you, you would see processes that are happening simultaneously. It's easier if there's only one source that's emitting at a time, but if you can actually look at techniques from radio astronomy, and they have methods for doing multiple source detection at the same time. So for a lightning discharge, a typical lightning discharge, really, you even tend to see that lightning discharge cover the entire sort of hemispheric field of view of the interferometer, from right to left. Yeah. Or just sort of spatially covering its sort of azimuth elevation field of view. Yeah. You don't want it to saturate, in terms of amplitude.
No, that's how you burn things.
Yeah. Yeah, or just you avoid being able to cross-correlate the peaks and the fluctuations.
And so cross-correlate is one of the things I was hoping you would say, because in order to find things in time from different directions, usually the cross-correlation shows you which direction you're coming from. Is that kind of right?
Let's see. That's not how I'm familiar with processing the time of arrival stuff that I normally work with, but you can certainly frame it as a cross correlation.
Well, maybe I should ask the question the correct way. What kind of signal processing do you do on your data?
Oh, yeah. So time difference of arrival processing with the non-interferometer data is done with a Levenberg-Marquardt algorithm. It's a nonlinear least squares retrieval given a bundle of time of arrivals that come from the same point, and a sort of test solution that you iteratively refine to match the observed arrival times. And so when it comes down to it, it's a least squares retrieval problem. And then you also have the trouble of matching up which lightning pulses or which detected pulses go together. Mm-hmm. And we get around that. Computers are fast enough that you can kind of get around that in a brute force way without even being too smart about it and just checking all the combinations.
What about the impulse detection? Do you have special techniques for that, or is it just before it was quiet and now it's loud?
Yeah, so there's an instrument that was the instrument that I use regularly was invented at New Mexico Tech in the late 1990s, and it combines a radio receiver that's digitizing that AM noise we talked about earlier. It does that very fast at about 25 megahertz, and every 80 microseconds it records the time of the peak pulse that arrived at the antenna in that 80 microsecond window. And so what allowed that instrument to work well is the ability to combine a digitizer, which has been around for a while, with a GPS timing reference that's precise enough to allow us to work on lightning timescales. And so there's some custom electronics that do the peak detection within that 80 microsecond window, and then that gets sent along with the GPS time into a little Linux computer that is at every site and writes the data to a hard drive using a very sort of conventional approach from there. And then those are connected by the internet, and we get the data back, and we can actually watch this in real time. So this is really fun when I have a thunderstorm here in West Texas. There's a server I have that collects data from each of the stations streamed in real time, and that least squares retrieval process we just talked about runs fast enough that we can watch on a display. The way I like to describe this is like you see a lightning flash happen outside. It'll show up on the display with its branched channel structure, and then you hear the thunder from it.
That would be kind of a fun Saturday afternoon.
It really is, yeah. It's you can sort of play a game like is that loud one I just heard? Is it a really large lightning flash? Oh yeah, there it is, and so it's a fun find the flash game.
So switching gears for a second, ball lightning, which we brought up in Lightning Round. Mm-hmm. But Nick has another question about it, kind of the same as mine, is it real? And what is it? And I guess the real question I have is, if it is real, what is it?
I don't think we know. It's one of those where we have one of those phenomena where we have reliable reports of it that date back hundreds of years, and yet it's rare enough that we can't really design an experiment to go out and observe it in any sort of scientifically organized sort of way. There's been attempts in laboratories to send a bunch of current through things like silicon plates or other materials that lead to these sort of stable plasmas that kind of roll along the floor. And so you can produce some things in laboratory settings that behave a bit like ball lightning, but precisely what is going on there that leads to the full scale phenomena that we observe in the atmosphere is not real clear. I'm not even sure we could say definitively exactly what scale it is. Although you hear reports of, for instance, the ball lightning moving through a window, or so it's maybe about that size.
They're just ghosts.
Could be ghosts. Could be ghosts. Ghosts with a love of physics.
But there are weird lightning phenomena beyond normal lightning that have been reliably observed, such as the things at the top of thunderclouds that have been photographed from the space station.
Yeah, that's right. Yeah, there's sprites and blue jets and elves and halos. This whole collection of creatively named things. So sprites take place when you have a whole lot of charge moved around in a regular thunderstorm discharge. So one of these very largest discharges, and that moves so much charge that the electric field in the ionosphere changes enough that the ionosphere breaks down and you get a secondary lightning discharge in the ionosphere. And so that's what a sprite is.
So it's lightning that goes up.
It's not even connected. The sprites aren't even connected to the regular thunderstorm except through the field aloft changing because the thunderstorm changed. Now there the other things like blue jets and gigantic jets. Those are lightning discharges that go up, and you can think of those as like a ground strike, except the thing that's being struck is the ionosphere.
Is the ionosphere grounded? I mean, why would it? Why would it?
It's a differently charged region.
Yeah, I guess so. It's just you don't think about that because you're like, oh well, it hits ground, and ground is important because
but
it's
there's cloud
ground.
to cloud lightning too.
Yeah, and so it's cloud to ionosphere lightning. All right, I sort of buy it, but I think you might be making it up.
I could be. You can next time when AGU returns, the American Geophysical Union has its annual meeting every year in San Francisco, and you should come hang out with all the lightning people. There's a set of sessions there every year in San Francisco.
Yeah, you definitely want us there to heckle.
Absolutely.
One of the things that got me interested in lightning and how it was formed was this book called The Cloudspotter's Guide. Are you familiar with it?
I have seen it. Do I have? I'm looking behind me on my bookshelf here.
It's by Gavin Pretor-Pinney. Luckily, he doesn't listen to the show, so I can totally butcher his name.
Yeah. I don't think I see a copy of it, but I've definitely heard of it. Yeah.
One of the stories it had in that book and in another book that was similar was of a pilot who ejected from his plane after hitting a storm unexpectedly and was in his pilot chair, a military pilot, so jet chair. Mm-hmm. And he fell, and the updraft kept lifting him up, and then he would keep falling and going up and back and forth for 40 minutes. Is that plausible? Have you heard
That's
of that?
extreme, no doubt. I've heard this story, yeah, and I tend to believe pilots when they've gone through something like that. I would consider that as reliable of a lay report as you could get, and I don't know the case in a great amount of detail, but the idea that someone could be carried up and down through a thunderstorm for that amount of time, yeah, that's not implausible, and certainly sounds miserable.
You don't want to try it?
No.
I mean, it did sound kind of miserable because I guess he almost drowned at one point, and he broke some pieces.
I think it's also very cold.
Yeah, frostbite too. But if you were prepared, wouldn't it sound like fun?
No.
Only me, huh?
No, sounds dangerous. There was actually a storm penetrating aircraft. It was an old T-28 piston engined plane that had all of its leading edges on the wings and things up armored, and so they would fly that through up to I think 1 inch hail and fly right through the updraft in a storm. One of the pilots of that now is also still an active scientist and does a bunch of work in high-speed lightning photography and videography, which is useful for studying lightning physics. So there is actually ways to go get inside the Thunderstorm. That aircraft has since been decommissioned, and there's been talk of bringing an A-10 aircraft into service for that role, but budgets being what they are, it's maybe tricky to get that project completed.
You're going to have to start telling people how important it is to study lightning and how it will save lives, and stop telling them you're doing it because it's so damn cool.
Yeah. Yeah, the ability to measure inside a thunderstorm is so important because you can do some things with remote sensing with radars, but there's nothing like an in situ verification where you can actually look at the population of ice crystals and grapple and supercooled water and really figure that out. It turns out to have importance for climate studies as well, even where if you want to know how much of the clouds are a big component of the Earth's radiative energy budget. And so if you want to understand climate change, you need to understand how clouds are comprised and exactly how long wave and short wave radiation is going to interact with those clouds as part of the climate system.
You've said supercooled water a few times. And so supercooled water is water that is cold enough to freeze, but it can't, because water kind of needs a catalyst to freeze, where a catalyst is less of a chemical here and more of just like a dust particle or a little tiny molecule it can glom onto, and then it starts building its crystal. But supercooled water won't crystallize on its own. Is that all right?
Yeah, you got that exactly right. That's until a water droplet that's pure water gets down to about minus 38 to minus 40 Celsius. It'll remain in liquid form, and then once it gets that cold and colder, it'll homogeneously freeze.
And so it's important that we keep the atmosphere very dirty so that we get lots of our clouds back?
I wouldn't exactly advocate that. I would. You could ask folks that lived in London at the during the start of the Industrial Revolution if they enjoyed the atmosphere being kept dirty. It led to a lot of fog, but
we're doing
maybe
quite
not
well
fog
here
that you
right
wanted
now.
to breathe.
So,
yeah,
I can't see the tree across the street. So,
well, that's.
Oh, you've got the big wildfires.
We're not anywhere near them, but we are getting the smoke. I feel a lot more for the people who are actually near them.
Yeah, it's those are some scary fires and real tragic situation there.
Okay, let's go back to discussing fun things.
Yeah,
for a little while. And so one of the things I wanted to ask you about was this weather balloon thing. You go out in the middle of a storm with the weather balloon, and I assume there's a key attached to it, like reenacting Ben Franklin's thing.
Yeah, it's Ben Franklin, but we let go, and that allows us to keep doing this in a university setting. These are big balloons that we launch into thunderstorms, and this was my undergraduate and graduate research in Oklahoma. Dave Rust, who passed away a couple years ago, was the sort of leader of this effort to do atmospheric electricity ballooning in Oklahoma, along with Don McGorman. These are big balloons. They're about 20 feet long when we launch them. They're usually we would launch polyethylene balloons. It's a very thin polyethylene, basically a large garbage bag that we inflate with helium, and it gets launched out of a launch tube. We inflate it in the back of a U-Haul truck and chase storms with a U-Haul truck, which is its own interesting experience.
Why are you renting our truck today?
Yep, and then there would be the service call, like, no, seriously, we really do need good tires on this. We're not just moving to bed today. We'd chase with that and a couple other vehicles for data collection. And launch this big balloon into a cloud. It has what's called a radiosonde on it, which measures pressure, temperature, and humidity and gives us position information as the balloon flies through the cloud. And then at the very very tail end of the train of instruments hanging off the balloon is an electric field meter that we use to measure the vector electric field inside the cloud.
And by electric field meter, you mean basically a metal marble?
It's two marbles attached to a spinning rod, and those marbles are made of aluminum. And just like our flat plate lightning antenna, those metal spheres are attached to a charge amplifier circuit, and as those spheres spin in the thunderstorm's electric field, charge is induced on those spheres back and forth, and the charge amplifier digitizes that signal, and that gives us a measurement then that's proportional to the electric field in the cloud.
Does it try to radio the signal to you, or do you collect the whole apparatus afterwards?
It does both. So the original version of the instrument actually sized those spinning spheres so that they were the right size to radiate in the 400 megahertz radio band that's used for meteorological instruments. That's since been re-engineered to put a proper transmitter separate from the spinning spheres. So we collect the data in real time that way, and then the data is also recorded on board, and that's a perfectly clean signal that's recorded and doesn't have any transmission noise and things in it. So we also try and retrieve those instruments that way.
So the two spinning balls, I'm assuming they don't go at a constant rate because they're being essentially pushed around by the electric field of the storm. Is that right?
No, they're driven by a motor. So they do spin at a constant rate, and that helps us as in doing the signal processing, because we can also then record a reference for the spin rate and then use that to it's called demodulate the electric field signal that's recorded.
And by demodulate, that is every time it goes in a circle, it gets a different view of the world. And so it kind of forms a sine wave. If you had charge on one side and none on the other, it would be high, low, getting lower, 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 low, and then back to high, and you'd be going around in a circle. And so your data would look kind of like a sine wave on one channel, and on the other channel, it would look like a sine wave that was exactly 180 off.
Yeah, exactly. And so you've described that perfectly. It's and then we record another sine wave from an accelerometer that's inside the spheres that tells us the position of the spheres, but we do that as a demodulation problem where we multiply the reference sine wave with the electric field sine wave, and use that to and then do some filtering to pull out the varying electric field.
And the accelerometer is because you might not be in a single plane. You're not spinning on a desk. You're in a 3D space. And so the accelerometer will tell you the tilt?
So the accelerometer is actually how we get the in phase and 90 degrees out of phase orientation of the spheres.
90 degrees, yes.
Yeah. Yeah, I guess 180 would, that'd just cancel us all out. But, so we have a 0 and 90 degree reference from the accelerometers that gives us the position of the spheres. They are spinning in a plane. And then the whole instrument platform also has, that also rotates, usually around a vertical axis. There's paddles on the end of that spinning rod that has the spheres attached to it. And that spinning, the aerodynamic forces on those pedals cause the instrument to rotate around at a slower rate than our spin rate. And so that's what allows us to get the vector electric field out of the charge that's induced on the spheres as it spins around.
And the end effect of this is you are taking a picture of the electricity in the whole cloud, and you end up with tree-like looking structures or more general pictures?
It gives you, the electric field variability in the cloud. You can use Gauss's law from our beloved Physics 2 class to infer charge density from how the electric field varies with height. And so that's how we know and verify what we think the charge structure is in thunderstorms. That normal tripole plus minus plus structure is something that you see in the fluctuations of the electric field. And then the other thing it tells us is the maximum electric field that we observe in clouds. And that maximum electric field is much, much less than the actual breakdown dielectric strength of the atmosphere. And so that's another one of the sort of enduring mysteries in lightning, is that we know roughly at what electric field lightning starts at, but it's not just a conventional dielectric breakdown that allows the lightning flash to get started. And so there's some high energy physics explanations for what might be going on there. Relativistic things even.
Really?
Yeah.
Okay, we're going to start the show over now for another hour where we talk about...
Tell us about relativity and lightning.
Yeah. So now this is where it would be great if I didn't have a meteorology background in Physics 1, but what I've learned from my colleagues over the year, you do observe X-rays and gamma rays that are emitted by lightning flashes. These are actually a source of noise for astronomers that are trying to do satellite-based detection of gamma ray bursts from astronomical sources, and that has something to do with probably the initial breakdown stage of the lightning discharge, and it's there's electrons that are accelerated in the electric field up to relativistic speeds, and that results then in these these higher energy emissions that are due to relativistic processes.
Cool.
Did you get all that? Can you explain it to me later?
Sure.
Okay, cool.
Lightning, thunderstorms are particle accelerators.
Oh, all right. Yeah, that's cool.
Yep, that's excellent. Yeah.
Is there such a thing as lightning tourism?
Lightning tourism.
I've never seen lightning with a Samsonite.
Yes, covers a lot of miles. I mean, and does so with low carbon emissions. So that's a plus. There are certainly storm chasing tours that you can get. A lot of those are based around trying to find a tornado and see some storm structure. There's folks that also do that from a more photographic point of view, where you want to be a little bit further away from the storm and get some good photos of it. Lightning's a part of that, and you could certainly. I'm sure there's good lightning photographs that are taken as part of those things. Is there some other kind of tourism you've heard of?
No, I just wanted to know where I could go to see lightning.
Yeah,
the web.
The web, Christopher. Last time there was a storm here and there was lightning, Christopher made me come inside right away. It was very sad.
That's
the right reaction.
Yeah, that's probably a safe move. And so the rare California thunderstorm, it's actually kind of a neat story. When the geostationary lightning mapper on the NOAA satellite was launched, it was built by the instrument itself was built by a team in Palo Alto and at Lockheed Martin, and they as they were doing that. As they were doing the initial instrument checkout, there happened to be a thunderstorm over California on the day when they were doing some of those initial checkouts. So they actually got the rare local lightning event right over where right overhead where the instrument was developed.
That is pretty rare.
If I recall, in the case you're talking about, we were at the beach and the lightning was striking the water.
Yeah,
oh boy.
But I'd already gotten out of the water. From Indrik, he says there is an Estonian proverb that goes, lightning keeps striking the same house. This is opposite to the English speakers, lightning never strikes the same place twice. Which one is more true?
Oh boy. Fascinating how science and culture sort of interact, or physics and culture interact to give these different impressions of things. So I wonder if that house that keeps getting struck is in if it were sitting on top of a hill, it would behave just like tall TV towers or radio towers that tend to wind up concentrating any lightning strikes in the vicinity to the location of those towers. And so perhaps it's a house in an unlucky location that winds up getting struck. But overall, I would say lightning, I would say is a fairly random process. And if there's nothing else to drive it any given direction, it's gonna move around pretty randomly.
Okay. So great answer. That was odd but interesting question. I have one more question for you before we let you go about your weekend. This one is from Stony Monster.
Who's that?
What powers will I develop if I get struck? Could you be specific? And what is the best way to get struck in order to get these powers?
I highly do not recommend that. So I
knew that would be the answer.
Dang it!
But there are major sort of if you survive a lightning strike, and people do, there are persistent neurological effects that include
X-Men powers.
No,
not X-Men powers, unfortunately. No, it's.
I shouldn't make fun. It is pretty bad.
I mean, yeah, that's it really does, leave people with debilitating injuries or depression or other things that, really is a significant impact on their quality of life. And there's even sort of things that the death statistics don't capture in terms of the impact of lightning on folks. So even as we've done a good job of reducing lightning deaths, those lightning injuries can still be really quite severe.
All
right. I'm chastened.
Yeah, come inside when it's lightninging.
Well, Eric, thank you for being with us. Do you have any thoughts you'd like to leave us with?
I would say that, if any of this sounds interesting to you, it would take as much math and physics as you can if you're a college student listening. And we always love having people that have an interest in instruments and in building hardware, that enlist in graduate programs to study this kind of thing. And the ability to make things and build instruments is just such an advantage, and maybe a skill that's a little bit too rare. So, if you have that kind of interest, I'd encourage you to go for it.
Cool. Well, our guest has been Eric Brunning, professor of atmospheric science at Texas Tech University. Thank you again for being with us, Eric.
You're welcome. I really enjoyed talking.
Thank you very much to our Patreon subscribers, both for Eric's mic and their awesome questions, including Nick, Tom Anderson, and Indrick, and KBX81. And I guess Stony Monster, although I feel a little weird because he's going to get thanked again. Special thanks to John Lehman of the Don't Panic Geocast for connecting us to Eric and for handing me some more questions. Wow, I didn't have to do hardly any work this week. Eric's episode on the Geocast was a lot of fun to listen to. Finally, thank you to Christopher for producing and co-hosting, and thank you for listening. You can always contact us at show@embedded.fm or hit the contact link on embedded.fm. Now, a quote to leave you with. This is from Bob Ross. In painting, you have unlimited power. You have the ability to move mountains. You can bend rivers. But when I get home, the only thing I have power over is the garbage. Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.